Somewhere right now, a foreign intelligence agency is copying your encrypted data. Not hacking it, not breaking it, just copying it, storing it, and waiting. They don't need to crack your bank records today. They only need to crack them eventually, and they're willing to wait a decade to do it. This isn't paranoia. It's a documented strategy with a name, and in the last 12 months, the math protecting nearly everything you do online quietly dramatically got weaker. Read that again. Not weaker because of a hack. Weaker because the number of qubits needed to break it just fell by an order of magnitude in less than a year. To understand why this matters, and why cybersecurity experts have started using a genuinely dramatic phrase to describe it, you first need to understand the single, unglamorous piece of math holding together nearly everything you consider secure online. Every time you check your email, log into your bank, or simply visit a website with a small padlock icon in the address bar, your device and that website are relying on something called public key cryptography, specifically two mathematical systems called RSA and elliptic curve cryptography. These systems work because certain math problems, like factoring an enormous number into its prime components, are essentially impossible for a classical computer to solve in any reasonable amount of time. Not difficult, effectively impossible. The kind of impossible that would take the fastest supercomputer on Earth longer than the universe has existed to brute force its way through. That impossibility is the entire foundation of internet security. It's the reason nobody worries about a stranger reading their bank statement as it travels across the internet, because breaking that specific kind of encryption isn't a matter of a clever hacker trying harder. It's a matter of physics and mathematics, making the task functionally unsolvable using the tools we currently have. Here's where the story turns, and where the phrase cybersecurity professionals have started using deserves your full attention. It's called Q-Day, and it refers to a single, specific, world-changing moment. The day a quantum computer finally becomes powerful enough to solve that supposedly impossible math problem. Not eventually, not theoretically, but actually, in practice, on real encrypted data. Nobody knows the exact calendar date this will happen. It isn't scheduled, and no such machine currently exists anywhere on Earth. But here's why the framing of a single, sudden day, rather than a slow, gradual decline, genuinely captures something true about how this specific threat actually works. Public key encryption isn't like a lock that gets slightly easier to pick over time. It's binary. An algorithm is either mathematically secure or it isn't, and the moment a sufficiently powerful quantum computer exists, that security doesn't degrade gradually. It flips instantly for everyone relying on that algorithm at once. This is not chaos. This is simply the nature of the mathematics involved. And it's precisely why the arrival of that specific machine deserves to be treated as a single discrete event, rather than a slow-fade security teams can comfortably watch unfold over years. Now, here's the part of this story that genuinely should concern you, because it isn't speculation. It's a measurable, documented shift that happened in real time over the past year. Back in 2019, researchers estimated that breaking RSA 2048, one of the most common encryption standards protecting internet traffic today, would require roughly 20 million qubits, an almost unimaginably large number, given that no quantum computer built anywhere has ever come remotely close to that scale. That number felt safely, comfortably distant, the kind of figure that let security experts reasonably assume this specific threat sat decades away, safely beyond anyone's immediate planning horizon. Then, in 2025, Google's own quantum research team published new work that dropped that estimate dramatically, down to under 1 million qubits. Read that again. In a single research update, the goalpost moved by more than an order of magnitude, and it didn't stop there. In a genuinely striking cluster of activity, 3 separate research papers, published within roughly 3 months of each other in early 2026, pushed that estimate down even further. According to detailed industry analysis tracking this exact shift, this specific run of research represents, in the words of one detailed report, the most significant shift in quantum threat assessment since Peter Shor published his factoring algorithm in 1994. Think about the weight of that specific comparison. Shor's algorithm, published over 3 decades ago, is the exact mathematical method a quantum computer would actually use to break this encryption in the first place. The foundational theoretical threat this entire field has been tracking since the 1990s. And this recent cluster of research, arriving within a single quarter of 2026, is being compared directly to that same foundational moment. The specific numbers behind this shift deserve to be stated plainly, because they're the heart of why the story genuinely matters right now, rather than at some comfortably distant future date. According to this recent research, breaking RSA encryption specifically might now require potentially fewer than 100,000 qubits under newer, more efficient architectures. A number that sounds almost unbelievable next to the 20 million qubit estimate from just a few years earlier. And elliptic curve cryptography, the specific encryption standard protecting virtually every major cryptocurrency and the majority of digital signatures used across the internet today, dropped to potentially fewer than 500,000 qubits. Think about what cryptocurrency specifically represents here. An entire multi-trillion-dollar global asset class, built almost entirely on the assumption that elliptic curve cryptography is safely, permanently unbreakable. That assumption just got measurably documented, significantly weaker within the span of a single year. Before this story tips into pure alarm, though, it deserves exactly the same honest, grounding context this channel applies to every genuinely significant claim, because understanding the true scale of the gap remaining is essential to telling this story accurately rather than sensationally. As of 2026, the largest deployed quantum processor anywhere in the world holds approximately 1,180 noisy qubits. Read that number again and place it directly next to the lowered threshold of 100,000 qubits needed to actually break RSA encryption. Even after the most dramatic resource reduction estimates published this year, the gap between today's most powerful working quantum computer and a machine genuinely capable of breaking real-world encryption remains roughly 2 full orders of magnitude, a 100-fold difference in scale. This is not chaos. This is the honest, necessary counterweight that separates a responsible telling of this story from pure fear-mongering. Q-Day has not arrived. No cryptographically relevant quantum computer exists today. And building one still requires clearing an enormous, genuinely difficult engineering gap, not simply a modest improvement on existing hardware. So why should any of this genuinely worry you today? If the actual machine capable of breaking your encryption remains years, possibly a full decade or more, away from existing, this is precisely where the second half of this story becomes considerably more urgent than the raw qubit numbers alone might suggest, and it involves a strategy with a genuinely unsettling name. One security researchers have been documenting as an active, ongoing threat rather than a distant future risk. It's called Harvest now, decrypt later, and in understanding exactly how it works reveals why the true deadline facing your own personal and financial security isn't actually Q-Day itself. According to cybersecurity analysis from firms tracking this exact threat, nation-state adversaries are already, right now, collecting and storing enormous quantities of encrypted internet traffic, banking transactions, medical records, government communications, corporate secrets, not because they can read any of it today, but because they're patiently betting that a sufficiently powerful quantum computer will eventually exist, and when it does, all of that carefully archived, currently unreadable data becomes instantly, retroactively exposed. Think about what that specific strategy actually implies for anything you've ever encrypted and sent across the internet, going back years. If an adversary copied that specific piece of data at any point while it was in transit, the security clock on it didn't start ticking the moment Q-Day finally arrives. It started ticking the moment that data was first intercepted and archived, regardless of how far in the future the actual decryption capability eventually materializes. This is exactly why security researchers keep emphasizing something called Mosca's theorem, named after Dr. Michele Mosca, co-founder of the Institute for Quantum Computing at the University of Waterloo, one of the most frequently cited, most respected voices in this entire field. The theorem is deceptively simple and genuinely worth understanding because it reframes the entire urgency of this story in a way raw Q-Day timelines alone can't fully capture. If the length of time your data needs to remain genuinely confidential, plus the length of time it takes your organization to fully migrate to quantum-resistant security, adds up to more time than remains before Q-Day actually arrives, you are already, right now, too late. Read that again and sit with exactly what that math implies for any organization holding on to genuinely long-lived secrets, medical records that need to stay private for a patient's entire lifetime, government intelligence that needs to remain classified for decades, corporate trade secrets meant to stay protected indefinitely. For exactly this kind of long shelf life data, the true effective deadline isn't some distant future date when a quantum computer finally gets built. It's today, minus however long your own migration to safer encryption actually takes to complete. Mosca himself has put actual numbers behind this specific risk, offering probability estimates that deserve to be stated precisely because they capture the genuine expert-level uncertainty surrounding this entire question far better than a single confident prediction ever could. According to his own published estimates, there's roughly a 1 in 7 probability that Q-Day arrives by the end of 2026, and a 50% probability it arrives by 2031. Think about what a coin flip probability by 2031 actually means for anyone planning security infrastructure meant to last for years. This isn't a distant, comfortable next-generation problem. It's a genuine, immediate planning consideration, the kind serious organizations are already treating as an active engineering deadline rather than a theoretical academic debate. The Global Risk Institute's own annual quantum threat timeline An industry standard expert survey drawing on assessments from leading physicists and cryptographers across the field places roughly a 1 in 4 chance of a cryptographically relevant quantum computer existing by 2030, and roughly a coin flip probability by 2035. Governments around the world have begun responding to these specific numbers with genuine, dated, verifiable urgency, and tracking that response reveals just how seriously institutions with access to considerably more classified information than the general public currently treat this threat. In the United States, federal agencies formally declared 2026 the year of quantum security, a genuinely significant institutional designation, not the kind of language a government casually applies to a comfortably distant theoretical risk. Canada has mandated that all federal departments submit formal post-quantum cryptography migration plans by April of 2026. The European Commission has mandated that member nations submit their own national transition roadmaps by December of that same year. Think about the specific pattern emerging across these 3 separate, entirely independent government responses, all converging on essentially the same narrow window of urgency within the exact same 12-month period. Governments don't typically coordinate this kind of simultaneous, mandated institutional action around a threat they genuinely believe remains decades away. There's a specific detail worth sitting with here, one that speaks directly to just how seriously this threat is actually being treated behind closed doors, beyond what's visible in public research papers and industry estimates. According to reporting on this exact issue, the United States government, which has access to classified intelligence specifically covering China's own quantum computing programs, information the general public simply doesn't have visibility into, appears to be acting as though the real, true timeline is considerably shorter than the public estimates already circulating throughout this video. Read that again, and consider what it means for the honest, complete picture of this threat. Everything covered so far in this video, the falling qubit estimates, the expert probability curves, the government migration deadlines, is drawn entirely from publicly available research and publicly announced policy. And even working purely from that public information, the level of institutional urgency already visible is genuinely striking. The fact that classified intelligence may be pushing that urgency even higher, behind doors most of us will never see through, deserves to be acknowledged honestly, even without pretending to know exactly what that classified information actually contains. Fortunately, this entire story isn't purely one of looming, unaddressed threat. And understanding the actual concrete defense already being built matters just as much as understanding the danger itself. In August of 2024, the National Institute of Standards and Technology, the USNO, government agency responsible for setting official cryptographic standards, finalized a specific set of new encryption algorithms designed explicitly to resist quantum computer attacks, known formally as FIPS 203, FIPS 204, and FIPS 205. Built on entirely different mathematical foundations than the vulnerable RSA and elliptic curve systems currently protecting most of the internet. These new standards aren't theoretical academic proposals anymore. They're the actual specific defense now being rolled out across government and industry, and understanding this rollout reveals that the response to this entire threat is a genuine engineering problem with a genuine, actively unfolding solution, not simply a looming disaster nobody's doing anything about. In the United States, specifically, National Security Memorandum 10 mandates that federal agencies complete their migration to these new quantum-resistant standards by 2035, a genuinely enormous undertaking given just how deeply RSA and elliptic curve cryptography are woven into essentially every piece of digital infrastructure currently operating, every website, every piece of enterprise software, every embedded device quietly running in the background of modern life. Think about the sheer scale of that specific migration challenge for a moment, because it's easy to underestimate just how difficult replacing this kind of foundational infrastructure actually is. Every website using HTTPS, every corporate virtual private network, every piece of enterprise Wi-Fi security, every digital signature verifying that a piece of software genuinely comes from who it claims to come from, all of it currently relies in some form on the exact mathematical systems this entire threat targets. Migrating away from that infrastructure isn't a simple software update pushed out overnight. It requires updating cryptographic libraries embedded across an almost unimaginably vast, interconnected web of hardware and software. Much of it decades old, much of it running on systems nobody has meaningfully touched in years. This is precisely why security researchers keep repeating a specific, urgent message, one that deserves to close out the practical, actionable core of this entire story. The uncertainty surrounding exactly when Q-Day will arrive should itself be treated as a motivator for immediate action, not a reason for continued delay, given both the genuinely lengthy timelines these kinds of infrastructure upgrades typically require. and the extreme sweeping impact a full breakdown of conventional cryptography would have across essentially every digital system currently in operation. Consider, too, just how quickly the underlying scientific foundation for this entire threat has been advancing in parallel, because it directly reinforces exactly why this specific window of urgency matters right now, in 2026, rather than at some comfortably distant future point. Google's own Willow quantum processor demonstrated a genuine, independently significant breakthrough in error correction in late 2025, showing that as a quantum processor scales up in size, its error rate can actually decrease rather than increase, a milestone physicists had chased since the 1990s. This specific achievement is precisely the kind of foundational engineering progress that shifts quantum computing's broader trajectory from what industry analysts describe as decades away toward something considerably closer, years away. IBM's own published roadmap targets large-scale, fault-tolerant quantum computing architecture by 2029, a specific, dated engineering target the company has been working toward methodically for years, rather than a vague, aspirational promise. Think about what it means that this entire quantum threat timeline isn't sitting still while security teams slowly prepare their defenses. The exact same underlying hardware progress, driving genuinely exciting quantum computing breakthroughs in medicine, material science, and scientific research, is simultaneously, unavoidably, the same progress shortening the runway available to migrate away from vulnerable encryption before that progress eventually turns into a genuine capability to break it. So where does the honest, carefully researched answer to this video's own title actually land? Could quantum computing genuinely break the internet? The evidence gathered here supports a considerably more precise, considerably more nuanced answer than a simple yes or no, one that respects both the genuine documented urgency behind this story and the genuine remaining distance separating today's hardware from tomorrow's actual threat. No quantum computer capable of breaking real-world encryption exists anywhere on Earth today, and the gap between today's largest working quantum processor and the machine that would actually be required remains substantial, roughly 2 orders of magnitude by even the most aggressive recent estimates. But the resource threshold required to eventually cross that gap has fallen dramatically, measurably, and repeatedly throughout the past year alone, a shift serious researchers are comparing directly to the most significant theoretical development in this entire field's history. And the true, practical deadline facing your own personal and financial security isn't actually Q-Day itself. It's considerably earlier than that, set by exactly how long your own sensitive data needs to remain confidential, combined with exactly how long the necessary migration to quantum-resistant encryption genuinely takes, a calculation that, for a great deal of the world's most sensitive, longest-lived information, already places the effective deadline uncomfortably close to today, regardless of when the actual quantum computer capable of exploiting that vulnerability finally gets built. This isn't a story about a single dramatic future event suddenly breaking the internet overnight, the way a headline like this video's title might initially suggest. It's a story about a quiet, genuinely urgent, already actively unfolding migration playing out right now, largely invisible to most people, going about their ordinary digital lives, driven by government mandates, finalized cryptographic standards, and a genuinely rare, cross-institutional consensus that the old assumption that this specific threat could comfortably wait another decade or two before requiring serious attention no longer holds up against the actual measured pace of quantum computing's recent progress. The internet isn't broken yet. But the mathematics that has quietly protected it for the better part of 3 decades just got measurably weaker in the span of a single year. And the organizations paying closest attention to that shift aren't waiting around to find out exactly how much weaker it eventually becomes. If you want to understand exactly what happens once your own everyday digital life, your bank, your email provider, your favorite websites, finally completes its own migration to quantum-resistant encryption, and what that transition actually looks like from the inside as it unfolds over the coming years, that's precisely the story we'll be tracking closely as it continues to develop. So make sure you're subscribed before that transition fully arrives. Before you go, I want to know what you honestly think about everything you've just heard. Does the dramatic, documented drop in the qubits required to break modern encryption over just the past year genuinely convince you Q-Day is arriving faster than most people currently realize? Or does the sheer remaining gap between today's largest quantum computer and the machine actually required to pose a genuine threat tell you this remains, for now, a distant, manageable problem rather than an urgent one? Leave your honest answer down in the comments below, and as always, I read every single one.